Welcome to the deep dive. I'm really glad you could join us today. We're about to embark on, well, a pretty comprehensive exploration into one of the most powerful tools out there for modern web development, ASP.NET. This deep dive, like all our explorations, is presented by Knowledge Flow. We're aiming to give you that shortcut, to being genuinely well-informed.
Absolutely. Our mission here is really to cut through the complexity. Web development can be dense, especially with something as robust as Microsoft's ASP.NET. We'll be pulling out the most important nuggets of knowledge, trying to get past the jargon, deliver the core concepts and practical insights, and best practices you can actually use to build dynamic web apps.
And by the end of this, you should walk away with a really solid foundation in modern web development. You'll understand not just what ASP.NET is, but maybe why certain choices were made architecturally, and hopefully how to apply these powerful tools in the real world. We've got a few surprising facts lined up, maybe just enough humor to keep things moving. So let's jump right in.
Okay, let's unpack this then. For anyone who's heard the name tossed around but isn't totally sure, what exactly is ASP.NET? It crops up everywhere in Tech Talk, but what's behind the name?
Right. So at its heart, ASP.NET is Microsoft's open source server-side web application framework. Think of it like a big toolbox, a really comprehensive construction kit, specifically for building dynamic web pages. And not just pages, but a whole range of web applications, complex web services too. Its main job really is to give developers the power to create pretty much any web experience they can imagine. Simple blogs, huge enterprise systems, you name it.
Okay, makes sense. So when did this powerful framework first show up? I know it's been around a bit, but where did it come from? What are its roots?
Good question. It first saw the light of day back in January 2002. That was version 1.0, and it arrived as part of the bigger .NET framework launch. It was the direct descendant, you could say, or maybe a much more capable evolution of Microsoft's older tech called Active Server Pages, ASP. It kept the idea of dynamic pages, but honestly, it was a massive leap forward. Capabilities, performance, architecture, all way beyond classic ASP. And something really foundational about ASP.NET right from the start, and still true today, is that it's built on the Common Language Runtime, the CLR. Imagine like trying to build a huge software project where every team had to use the exact same programming language. Super restrictive, right? The CLR is kind of like a universal translator and engine. It lets developers write ASP.NET code using any supported .NET language, C#, Visual Basic, even F#. That freedom was a huge deal for teams. Yeah. Also, back then, the ASP.NET SOAP extension framework was pretty important. It handled SOP messages, which was the standard for web services communication at the time. What's really interesting, though, is how it keeps getting re-implemented. It's not just small updates. We're talking major architectural shifts. It's constantly embracing a more modern, modular, open-source way of doing things. This evolution lets it plug in nicely with other modern frameworks, like Entity Framework for data access, and the open-source part means faster innovation, community contributions, all that good stuff.
That makes a lot of sense. Like, the framework itself is adapting, evolving. Which brings me to the next point. This is where it gets really interesting. How did this powerful tool evolve from those early days to what we see now? Tech rarely just appears fully formed, right? There's always a story.
Exactly. So, starting in 2002 with the .NET framework, ASP.NET immediately set itself apart from classic ASP. The big difference was compiled code for dynamic apps. That meant way better performance, more robust applications, compared to the old interpreted script model. In those early years, ASP.NET Web Forms was definitely the dominant player. It was, ambitious. It tried to mimic desktop app development for the web, drag-and-drop controls, abstracting away HTML and HTTP. It was innovative, yeah, but maybe showed us what not to do in terms of hiding web standards. It kind of paved the way for better approaches later on. But the web, it never stands still. Demands on frameworks kept growing. And that led to a pretty significant shift around 2009, the introduction of ASP.NET MVC, Model View Controller. Imagine a big app where your database code, UI stuff, business rules all tangled together. Fixing a simple UI bug could, accidentally break how you save data. Not good. MVC's separation of concerns was like untangling that mess, giving each job data, presentation, logic its own clear space. Made apps much easier to manage, test, and scale. Scott Guthrie at Microsoft, he was a key figure here. Product Unit Managing Director for ASP.NET. He really drove that rapid development pace, leading up to version 1.1 and beyond.
All right, so MVC was huge, addressing a real pain point. But what about the biggest shift? You mentioned ongoing evolution.
Oh, the biggest leap, without a doubt, came in 2016 with ASP.NET Core. That was monumental. The framework became fully cross-platform, truly open source. Suddenly, developers could build and run ASP.NET apps not just on Windows, but on Linux, on Mac OS too. Huge expansion. Since then, ASP.NET Core has really leaned into modern web standards. It's become the go-to for things like microservices, cloud-native development. These continuous improvements have massively boosted performance, flexibility, its relevance in today's web world. It's a real story of continuous innovation.
Fascinating history. So let's break it down. What are the core components, the fundamental concepts that underpin all ASP.NET development? If someone's diving in, what are the building blocks they really need to get?
Yeah, understanding the core structure is key to appreciating its power. It's a really well-designed framework for Microsoft, built for dynamic web apps and services. It offers a whole set of capabilities, starting with its main architectural styles or paradigms. First, you've got web forms. That's the traditional event-driven model we touched on, designed to feel a bit like desktop development, abstracting away some HTTP stuff. And then there's MVC, Model View Controller. Provides that clear separation concerns we talked about, improves maintainability, testability, super important. For building RESTful services, for communication between different apps or front ends, there's Web API. Razor Pages came along later. It's a simpler, page-focused model, really good for apps where the logic is tied closely to individual pages. And the newest big thing is Blazor. This lets you build client-side UIs using C# directly in the browser, using WebAssembly. That's a potential game changer for C# devs wanting to do interactive front ends without heavy JavaScript. Okay, beyond those architectures, there's some core concepts that pop up everywhere in ASP.NET. Server-side processing is fundamental.
All the complex logic, data stuff, security checks that happens on the server before HTML gets sent to the browser keeps the client light. State management is crucial because the web is stateless, right? HTTP doesn't remember anything between requests. So ASP.NET gives you tools like view state and web forms, session state, cookies, query strings, ways for your app to remember things about the user session. Routing is how ASP.NET figures out which code to run based on the URL the user requests. It makes for cleaner, more user-friendly URLs. And dependency injection, or DI. This is a really powerful pattern. It helps make your code modular and easier to test by decoupling components. Think Lego bricks DI lets you snap in the right piece when you need it instead of hard coding connections. And specifically within the modern stuff, ASP.NET Core, there are some standout features. Cross-platform support, obviously, on Windows, Linux, macOS. Huge deal. The middleware pipeline is super powerful. Imagine every web request going through a series of checkpoints. One handles authentication, another logging, maybe one compresses the response. You configure this pipeline to control exactly how requests are processed. Really fine-grained control. Configuration and logging are very robust. Easy ways to read settings from files or environment variables, and great integration with the logging tools. And security is baked in deep. Strong tools for authentication, who you are, authorization, what you can do, protecting against common attacks, and finally, data. Database and ORM support is strong. Entity Framework Core is the main ORM. It maps database tables to C# objects so you write less raw SQL. Massively simplifies data access. But if you need more direct SQL control or something super lightweight, Dapper is a popular alternative.
Wow, okay. That really paints a picture of a seriously versatile toolkit. It feels like there's something there for almost any kind of web project, any kind of developer. Simple sites, complex enterprise apps, the breadth is really impressive. You mentioned MVC was a pivotal moment. Let's zoom in on that a bit. It's such a foundational pattern, revolutionized how lots of apps are built. So what is it exactly, and why is it still so important today in the ASP.NET world?
Absolutely. ASP.NET MVC Model View Controller. Yeah, it's a framework Microsoft developed specifically for dynamic web apps. Its real strength is that structured approach. Separating concerns. That separation makes apps so much easier to manage, test, and scale, which, for any project beyond the very basic is critical. It really forced a better way of thinking about application structure.
So the core MVC pattern itself, it divides an app into three main distinct parts. First, the model. The model is all about the application's data and the business logic around that data. It talks to the database, often using an ORM-like entity framework. A model could be a simple C# class, a POCO, plain old CLR object just holding data, like a product class with ID, name, price, or it could be more complex, handling data validation, business rules, that sort of thing. Then you have the view. The view's job is purely about rendering the UI. It's what the user actually sees and interacts with in the browser. Views in ASP.NET MVC typically use Razor syntax. That's a templating engine letting you mix C# code right into your HTML. The view gets data from the model via the controller and presents it.
So using our product example, a view might show at model.name as a heading, at model.price, and a paragraph. It dynamically pulls those values. And the third piece is the controller. The controller is like the traffic cop or the orchestra conductor. It handles incoming user requests, manages the application flow. When a user clicks a link or submits a form, the request usually hits a controller first. The controller figures out what needs to happen, maybe call the model to get data, maybe update something. Once it has what it needs, it chooses the right view and passes the data to it for rendering. Controllers use action methods to handle specific requests. So a product controller might have a details action that takes an ID, gets the product from the model, and sends it to the details view.
That breaks it down really clearly. So how does it all flow together? When a user actually makes a request, say, clicks a link in an MVC app, what's the sequence? It sounds like a well-choreographed dance.
It is, yeah. It follows a pretty defined MVC request lifecycle. First step, when a request comes in, is request routing. The routing engine looks at the URL and, based on patterns you define, figures out which controller and which action method should handle this specific request. It's like the dispatcher. Once the route's figured out, it's controller execution. The routing engine calls the specific action method on the chosen controller. This is where your application logic really starts. Next up, potentially, is model interaction. If the action needs data, maybe to display product details or save changes, the controller talks to the model. Fetching data, updating whatever's needed. This step might be skipped if no data interaction is required. After the controller has done its work, possibly interacting with the model, it's time for view rendering. The controller selects the appropriate view and passes any necessary data to it. The view then uses that data, combined with its HTML and Razor code, to generate the final UI, and the last step is response set. The fully rendered HTML, plus any CSS, JavaScript, etc., gets sent back to the user's browser to be displayed. That completes the cycle. ASP.NET MVC has several key features that make it powerful. That separation of concerns is number one. Just makes code so much cleaner. Routing is super flexible. You can create nice, clean URLs without file extensions. Good for users, good for SEO. Model binding is a huge time saver. It automatically takes data from the incoming request like form fields or query strings and converts it into strongly typed C# objects for your action methods. Less manual parsing. Filters and attributes are cool too. They let you declaratively add logic that runs before or after action methods, things like checking if a user is logged in, authentication, logging a request, or caching results. For passing small bits of data between the controller and view, or between requests, you have things like temp data, and viewback. Each has slightly different uses. And critically, scalability and testability are core benefits. The separation makes it much easier to write unit tests for your controllers and models, often using frameworks like XUnit or Monk. Dependency injection fits right in here too. So the advantages boil down to a few key things. Better code organization, definitely. Easier to maintain over time.
Testability is a massive plus. Being able to test logic in isolation is crucial for robust apps. Customizable routing gives you those clean, SEO-friendly URLs. It also naturally supports RESTful APIs. You can easily build web APIs within an MVC project. And it's generally considered a lightweight framework, especially compared to web forms. No view state, no complex post-back lifecycle. That usually means faster, more efficient applications.
Okay, so if MVC offers that really robust structure, that clear separation, what gaps did Razor Pages fill when it arrived in ASP.NET Core? It sounds like maybe a different philosophy for different kinds of problems.
That's a great question. Because MVC is powerful. But sometimes, for simpler, more page-focused scenarios, it can feel like, well, a bit much. Maybe too much ceremony, too many files. Razor Pages came along in ASP.NET Core 2.0 as a lighter-weight, page-centric alternative. The idea was to simplify development by putting the page's logic directly with the page's view in a related code behind file. It's kind of closer to the original ASP idea, maybe, but with all the power and structure of .NET Core behind it. It's particularly good for apps where the UI and logic are very tightly coupled on a per-page basis. The basic structure is really simple. Each Razor page is usually two files, a .cshtml file for the view markup and a .cshtml.cs file for the code behind called the page model. It really leans into this convention over configuration idea, meaning if you follow certain file naming and location conventions, a lot of the setup, like routing, happens automatically. Less boilerplate code compared to setting up controllers and routes in MVC.
That sounds like it could definitely streamline things for certain projects. Can you paint a clearer picture? How is a typical Razor Pages app actually structured? It sounds like it's designed for easy navigation just by looking at the folders.
Yeah, it's very intuitive. Typically, all your web pages live inside a pages folder in your project root. Inside pages, you might have index.cshtml and index.cshtml.cs, that's your home page, automatically routed to the root URL. There may be a product subfolder. Inside that, index.cshtml for listing products and details.cshtml for a single product. The URL structure directly mirrors this folder structure, so products details would map to that details.cshtml page. It's very direct. And each page, as I said, has two main parts, the Razor page itself, the view, and the .cshtml file. This holds your HTML and uses Razor syntax @dead to embed C# for dynamic stuff. It usually starts with @page at the top. It might declare its model type like @model product details model. Then in the HTML, you can access properties from that model like h1 at model.product.nemo1. The second part is the page model, the code behind, in the .cshtml.cs file. This is a C# class inheriting from page model. This is where the logic for that specific page lives. Handling requests, interacting with data services, etc. It has handler methods, often named following conventions like onGet for handling get to request to the page, or onPost for handling form submissions via POST. Inside onGet, you might fetch data and set properties on the page model class itself, which the .cshtml view can then display. Razor pages have some neat features that make them efficient. Simplified routing is a big one. As we said, routing is mostly based on file location. No complex route definitions needed for basic cases. Model binding and data handling work similarly to MVC. The page model handles HTTP requests, DetT, PostT, etc., and model binding automatically maps incoming data to properties on your page model. It uses the same built-in tag helpers and Razor syntax as MVC views, which helps generate HTML elements cleanly. Things like form inputs, links, etc. Dependency injection support is first class. You can inject services like your database context or logging directly into the page model's constructor, just like in an MVC controller. And handling form submissions is very straightforward. You create an HTML form in your .cshtml file that POSTs back to the same page.
Then you implement an onPost method in your page model to handle the submitted data. You can use attributes like bind property to easily bind form data to page model properties. So the advantages are pretty clear for certain scenarios. Easier development for page-centric apps, definitely. Fewer files, less ceremony than full MVC. This often leads to improved readability and maintainability, especially on smaller teams or simpler projects, because the UI and its related logic are right next to each other. For small to medium apps, you might even see better performance potentially because there's slightly less overhead than the full MVC pipeline sometimes. And it comes with all the essential built-in features of ASP.NET Core. Authentication, authorization, validation, DI. It's all there.
It really does sound like a fantastic option for quicker, simpler development, especially if your application naturally breaks down into distinct pages. That feels like a real aha moment for efficiency, maybe getting something functional out the door faster. But I do wonder, does that page-centric approach ever become a limitation? Like if an app gets really complex with lots of shared logic?
That's a very fair point. And yeah, that's often the trade-off. Razor pages excel in simplicity for page-focused work. But for very large, complex applications, especially those with intricate business logic that needs to be shared and reused across many different views or workflows, MVC's stricter separation of concerns can sometimes provide better long-term organization and maintainability. It really comes down to choosing the right tool for the specific job. If your app is mostly a collection of distinct pages doing their own thing, Razor Page is probably great. If you have complex interactions, shared workflows, and need that very clear separation between logic, data, and UI across the board, MVC might scale better conceptually.
Right. Choosing the right tool. That brings us perfectly to a really pivotal question for developers today. ASP.NET Core, or the traditional ASP.NET framework. They share the name, but what's the fundamental difference? What do you need to know when making that choice?
Yeah, that's the big one, isn't it? It's a conversation that happens a lot. So yes, both are powerful web frameworks from Microsoft, but despite the shared heritage, they are fundamentally different beasts. They differ significantly in architecture, performance, where they can run, and their ideal use cases. It's less about one being universally better and more about understanding where each one really shines. Let's dig into those distinctions.
Okay, let's start with ASP.NET Core. That was the big reinvention in 2016. What makes it so significant? Why did Microsoft go down that path?
ASP.NET Core, yeah, it was a groundbreaking shift. It's a modern framework, completely redesigned from the ground up. The key things are, it's cross-platform and open source. The whole design philosophy was about high performance, modularity, and being lightweight. This makes it incredibly well suited for modern development practices, especially cloud-based applications and microservices architectures, where efficiency and flexibility are absolutely key. Let's look at its key features. The most transformative is definitely cross-platform. Runs on Windows, Linux, Mac OS. Huge flexibility deployment. It delivers high performance. The request pipeline is optimized. There's less overhead. That means faster apps, better scalability. It's modular and lightweight. Unlike the older framework, which was kind of monolithic, Core lets you include only the components you actually need. Uses middleware extensively. Keeps your app footprint smaller. Built-in dependency injection is a first-class citizen right from the start. Makes building modular, testable apps much easier. For web server support, it has its own high-performance server called Kestrel, but it can also run behind traditional servers like IIS or Jinx. More options. And being open source is huge. Development happens in the open on GitHub, lots of community contribution, faster release cycles, more transparency. So these features lead to some clear advantages. Cross-platform compatibility to deploy anywhere. Superior performance, great for demanding modern apps. Modular and scalable flexible architecture using middleware. Cloud-ready purpose-built for cloud and microservices. Open source benefits from community innovation and rapid updates.
Okay, so if you're starting a new project or maybe advising a business, when should you really lean towards ASP.NET Core? What are the clear signals to choose it?
Right. You should definitely choose ASP.NET Core if cross-platform support is a must-have. If you need to deploy on Linux, for instance. If high performance and using modern development tools and practices are priorities, Core is the way to go. If you're building cloud-based applications or microservices, Core is designed specifically for that world. And finally, if you prefer an open-source, community-driven approach with frequent updates, ASP.NET Core fits that model perfectly. For almost all new development, Core is the recommended path.
Makes sense. But what about the traditional ASP.NET framework? It's the veteran, been around since 2002. It must still have its place, right? It can't have just disappeared overnight.
That's a good point. It hasn't just vanished. The traditional ASP.NET framework, often just called .NET Framework, is indeed the established workhorse. It's been a robust, battle-tested solution for decades, but it's primarily designed for Windows-based applications. It built up a very rich ecosystem over the years for web apps, APIs, and particularly enterprise solutions deeply integrated with Windows. Its key features really reflect that Windows focus. It's Windows only, runs exclusively on Windows servers. It has broad support for older patterns like web forms, as well as MVC and Web API within its structure. For hosting, it primarily relies on ICE, Microsoft's web server, which is deeply tied into Windows Server. Database integration includes the original entity framework, not Core. It has a strong enterprise focus, especially for solutions needing tight Windows integration, like using Active Directory extensively. And it has robust security mechanisms built around Windows, like Windows authentication integrated with Active Directory. So its advantages come from that maturity. It's mature and stable, very well established, lots of enterprise support, proven over many years. Its full Windows integration is key for organizations heavily invested in the Microsoft ecosystem, Active Directory, Windows Auth, specific ICE features. It's the essential choice for legacy application support. If you're maintaining or extending an older app built on it, you often need to stick with it. And because it's been around so long, it has a vast ecosystem of robust libraries and tools, many third-party components specifically targeting it.
Got it. So for what specific scenarios would this established framework still be the go-to choice today? When would you consciously pick framework over Core?
Okay, you definitely choose the ASP.NET framework if you are maintaining or extending a legacy application built on it. Migrating can be a significant effort. If your application absolutely relies on Windows-specific features that don't have a direct equivalent in Core, maybe DEEP-COM and DUROP, specific Windows services, or very particular Active Directory integrations, if you need that mature, battle-tested framework for a specific compliance reason, or within a very conservative enterprise environment that hasn't yet moved towards Core. And, practically, if your organization is just heavily invested in the existing Windows infrastructure, specific Windows Server versions, IC configurations, tooling, and isn't ready or doesn't need to make the leap to cross-platform yet. Let's do a quick side-by-side to make it crystal clear. Platform. Core is cross-platform. Win, Linux, Mac OS. Framework is Windows only. Performance. Core is generally faster, more optimized. Framework is slower due to older dependencies like system.web. Hosting. Core is flexible. ISO, Kestrel, self-host. Framework pretty much requires ISO. Architecture. Core is modular, lightweight. Framework is more monolithic, cloud and microservices. Core is designed for this. Framework has limited suitability. Open source. Core is fully open source. Framework is closed source, though parts of .NET are open. Security. Core has modern enhancements, identity, JWT support. Framework leans on Windows Auth 8 integration.
That comparison really lays it out clearly. Makes it much easier, hopefully, for you listening to choose the right tool for your specific job based on project needs, future goals, and maybe existing infrastructure. It's really about that informed decision, not just following a trend. Okay, we've talked frameworks. Let's shift gears to something critical in almost any app today. How does ASP.NET handle talking to databases efficiently? Because that interaction is so often where performance bottlenecks happen.
You're absolutely right. Data access is crucial. And the primary tool for this in the modern ASP.NET world is Entity Framework Core, or EF Core. It's a lightweight, extensible, and cross-platform ORM that's object relational mapper. Its main job is to drastically simplify how you interact with databases. Instead of writing lots of repetitive SQL code manually, EF Core lets you work with your database using familiar C# objects. It maps your C# classes to database tables and translates your C# queries into SQL. This cuts down hugely on the amount of boilerplate data access code you need to write and maintain. EF Core is packed with features. Cross-platform support is key works on Windows, Linux, Mac OS, just like ASP.NET Core itself. It supports different development approaches. Code first is really popular. You define your database structure using C# classes, and EF Core can generate the database schema from your code. Or there's database first, where you point EF Core at an existing database and it generates the C# classes for you. LINQ queries are a massive feature. LINQ stands for Language Integrated Query. It lets you write database queries in C# using familiar syntax.
EF Core then translates these LINQ queries into efficient SQL for your specific database. Much safer and often easier than writing raw SQL strings. Change tracking is smart. EF Core automatically keeps track of changes you make to the objects you've loaded from the database. When you tell it to save, it knows exactly which records need to be inserted, updated, or deleted. Very efficient. Migrations are essential for managing database schema changes over time. As your application evolves, your database schema needs to change too. Migrations let you define these changes in code, apply them systematically, and even roll them back if needed. Keeps your database schema in sync with your application code. It also supports optimistic concurrency to handle situations where multiple users might try to edit the same data at the same time, helping prevent data loss. And importantly, these days, it has growing NoSQL database support, including providers for databases like Azure Cosmos DB.
Okay, that sounds powerful. For someone just starting out with it, what are the essential steps? How do you actually set up EF Core in an ASP.NET Core project to get it talking to a database? Seems like a few pieces need connecting.
Yeah, getting it set up is pretty streamlined once you know the flow. First step is usually installing the necessary NuGet packages. You need the Core EF Core package, a package specific to the database you're using, like Microsoft.Entity Framework Core.CalSQL Server for SQL Server, or MPGSQL.Entity Framework Core.PostgreSQL for Postgres, and the tools package for migrations, Microsoft.Entity Framework Core.Tools. Second, you create a custom DB context class. This class is central. It inherits from DB context and represents your connection to the database. Inside this class, you define DB set properties for each table you want to interact with. So you'd have public DB set products, get, are set. You also need to define your end classes, like the product class itself, with properties matching your table columns. Third, you configure dependency injection. In your program.cs or startup.cs in older templates, you register your DB context with a dependency injection container. This is where you tell EF Core how to connect to your database, usually by providing the connection string. You use methods like addDBContext and use kill server or use mpgsqll, etc. Fourth, you define the connection string. This string contains all the details needed to connect server name, database name, credentials. You typically store it securely in your appsettings.json configuration file. And finally, fifth, you run migrations. Using the .NET CLI, .NET EF, you run commands like .NET Air migrations at initial create to generate the first migration based on your DB context and entity classes, and then .NET F database update to apply that migration and actually create the database schema. These steps get everything wired up. Once that's done, basic data operations become really straightforward. Querying data? You can get all products with something like context.products.tollist. Or use LINQ methods like where, order by, first or default to build more complex queries in C#, adding data. Create a new product object in C#, add it to the context, products DB set, and then call context save changes. EF Core generates the SQL insert, updating data. Fetch the existing product using a query, modify its properties like product.price and new price, and call context, save changes. EF Core's change tracking figures out what changed and generates the SQL UP date, deleting data. Find the product you want to remove, tell the context to remove it, context.products.reproduct, and call context.save changes. EF Core sends the SQL delete. It really simplifies these common tasks.
And for building more maintainable, testable code bases, what about design patterns? You mentioned DI helps. How do people structure their data access with EF Core to keep things clean as the application grows?
That's a great question for long-term health. A very common and highly recommended pattern is the repository pattern. The idea is to encapsulate your data access logic behind an abstraction, an interface. So you define an interface, say iProduct repository, with methods like getAllProductsAsync, getProductBy desync, and addProductAsync, product, etc. Then you create a concrete class, product repository, that implements this interface. Inside product repository, you inject your application DB context and use EF Core to implement those methods. Your business logic layers then depend only on the iProduct repository interface, not the concrete implementation or EF Core directly. This decouples your application layers, makes testing much easier. You can mock the repository interface, and makes it easier to potentially swap out the data storage mechanism later if needed. It adds a layer, but often pays off in maintainability.
Makes sense. Okay, moving beyond just the application talking to its own database, modern apps often need to talk to other services. Mobile apps need data, single-page web apps need data, services need to communicate. That's where ASP.NET Web API comes in, right? It feels like the glue holding many modern systems together.
That's exactly. ASP.NET Web API is the framework within .NET specifically for building HTTP-based services. Its strength is its broad utility. It lets you expose functionality or data over HTTP in a standardized way so that pretty much any client browsers, mobile apps, iOS, Android, other backend services, SPAs, React, Angular, Vue, even IoT devices can consume it. It's particularly geared towards building RESTful services. REST, representational state transfer, is an architectural style emphasizing standard HTTP methods, get, post, put, delete, statelessness, and resource-based URLs. Web API makes building APIs that follow these principles very natural on the .NET platform. Web API has its own set of key features. It's designed to be lightweight and scalable, optimized for the high-performance needs of APIs. It embraces standard HTTP methods, get for retrieving, post for creating, put for updating, delete for removing, clear verbs for clear actions. It supports flexible data formats. JSON is the most common format for APIs today, and Web API handles JSON serialization and deserialization automatically, but it can also support XML or other formats if needed. Routing and attribute-based controllers provide flexible ways to map incoming URL requests to specific C# methods, actions, in your API controllers. You can define routes globally or use attributes directly on your controller actions. Dependency injection support is built in, just like the rest of ASP.NET Core, promoting modular and testable API designs. And crucially, it offers robust authentication and authorization mechanisms. You can easily secure your APIs using standards like OAuth 2.0 and JWT, JSON Web Tokens, to ensure only authorized clients can access protected resources.
So how does someone get started if you want to build a new API using ASP.NET Core? What are the practical steps to get that basic structure up and serving requests?
Setting up a new Web API project is really quick with the .NET templates. Step 1. Create a new project. You can use the command line, .NET new web API-in my cool API, or Visual Studio to create a new project based on the Web API template. This scaffolds a basic project structure optimized for APIs. Step 2. Create a simple API controller. This is where your API endpoints live. You create a C# class, typically inheriting from controller base. You decorate the class with attributes like route, API controller, which uses the controller name for the base route, example API products, and API controller, which enables helpful API-specific behaviors. Inside the controller, you define methods for your API operations, decorating them with HTTP method attributes like HTTP GET for retrieving data, HTTP POST for creating, etc. You usually define a simple data transfer object, DTO, or use your domain model class like product to represent the data being exchanged. Step 3. Configure the API in program.cs. The template usually sets up the basics, but you need to ensure services for controllers are registered, builder.services.add controllers, and that the routing middleware knows how to map requests to your controllers, app.map controllers. Step 4. Running the API. Just run your project .NET Run. By default, it will likely launch Kestrel and listen on HTTPS, example https.localhost.5001 or similar. You can then start sending requests to your defined endpoints, like https.localhost.5001 MP products. Now, implementing the standard CRU'd operations, create, read, update, delete, is fundamental for most APIs. For adding a new product, CoST, you'd create a method decorated with HTTP POST. It would typically accept a product object in the request body. On successful creation, it's a good practice to return a 201 created status code along with the location, URL of the newly created resource using created action. For updating PUT, you'd use HTTP put, ID, where I is a route parameter for the product ID. The method accepts the ID in the updated product data. You'd find the existing product, update its properties, save the changes, and typically return 204 no content to indicate success without sending back the whole object. For deleting, you'd use HTTP delete. The method takes the ID, finds the product, removes it, saves changes, and again usually returns 204 no content. Using these standard HTTP methods makes your API predictable and easy for clients to consume.
Right, makes sense. So once you've built these endpoints, how do you actually test them? Especially the post, pay, delete ones, you can't just type those URLs into a browser easily, can you?
Exactly. While you can test GET requests in a browser, for the others you need dedicated tools. Developers commonly use tools like Postman, Insomnia, or even command line tools like curl. These tools let you construct any kind of HTTP request. You can specify the method, post, put delete, set request headers like content typed application JSON, provide a request body, usually JSON payload for creating updating, and send the request to your API endpoint. Then you can inspect the full response, the status code, 200 OK, 201 created, 404 not found, etc., the response body, and headers. It's essential for verifying that your API behaves exactly as expected under different conditions.
And for critical applications, security is key. How do you typically secure a web API built with ASP.NET Core? Prevent just anyone from calling your delete endpoint, for example.
Absolutely critical. Very common and standard approach is using JWT, JSON Web Token, authentication. The process involves a few steps. First, you install the necessary NuGet package, Microsoft.ASP.NET Core.authentication.jwtbearer. Then, in your program.cs, you configure the authentication services. You call add authentication and specify JWTbearer defaults.authentication scheme. Then you call add JWTbearer and provide options, primarily the authority, the URL of your identity provider like Identity Server or Azure AD BDC that issues the tokens, and the audience, a unique identifier for your API, ensuring the token was intended for it. You also need to ensure the authentication and authorization middleware are added to the request pipeline, app.useAuthentication, app.useAuthorizaation, usually placed before routing. Once this is set up, you can protect your controllers or a specific action method simply by adding the authorized attribute. Requests without a valid JWT bearer token in the authorization header will automatically be rejected with a 401 unauthorized status.
Okay, as applications get bigger, managing all the pieces and how they connect, how they depend on each other, that gets really complex really fast. So what exactly do we mean by dependencies in ASP.NET, and how do we stop our code from turning into a tangled mess?
That's a perfect lead-in because, managing dependencies is crucial for avoiding that tangled mess scenario, often called spaghetti code. In ASP.NET, dependencies are essentially anything external that your code relies on to do its job. External components, services, libraries. Think of it like ingredients for a recipe. Your code is the recipe instructions, but it needs flour, eggs, maybe a specific spice blend. Those are the dependencies. Managing these effectively is absolutely key for building apps that are scalable, testable, and maintainable in the long run. And the primary tool ASP.NET Core gives us for this is its built-in support for dependency injection, DI. We can roughly group dependencies into a few types. Framework dependencies. These are core parts of ASP.NET itself that your app uses implicitly, like routing, configuration system logging. Service dependencies. These are usually your own custom classes that provide specific functionality. Things like a product service to handle product logic, a user repository to talk to the user database, an email sender service. Library dependencies. These are third-party packages you bring in via NuGet. Think Entity Framework Core, AutoMapper, Newtonsoft.json, Serlog external code you're relying on. Configuration dependencies. Your app often depends on settings, connection strings, API keys, feature flags stored in appsettings.json, environment variables, or maybe a secret manager. Managing all these types cleanly is what DI helps with.
Okay, so dependency injection, DI. We've touched on it, but let's really unpack it. What is it fundamentally, and why is it considered such a cornerstone of modern software development? It sounds like more than just a fancy term.
It really is fundamental. Dependency injection is a design pattern. The core idea is that a class shouldn't create its own dependencies. Instead, those dependencies should be injected or provided to it from the outside. Think of a product controller. Instead of creating its own product service instance inside its constructor, var service uProduct service, that's bad. It declares that it needs an iProduct service in its constructor parameter. ASP.NET Core's built-in DI container sees this request and automatically provides an instance of a class that implements iProduct service. The controller doesn't know or care how the service was created, only that it got one. This is called inversion of control. The control of creating dependencies is inverted, moved outside the class. The benefits are huge. First, improved maintainability. Because components are loosely coupled, they depend on interface abstractions, not concrete classes. You can change the implementation of a dependency without breaking the classes that use it, as long as the interface contract is met. Second, better testability. This is massive. Because dependencies are injected, you can easily inject mock or fake versions during unit testing. You can test your product controller logic without needing a real database by injecting a mock iProduct service. Makes tests faster, more reliable, and truly isolated. Third, it enhances scalability. Modular design naturally lends itself better to scaling. Components are self-contained units. And fourth, it reduces boilerplate code. You don't manually wire up object creation everywhere. You register your services once with a DI container, and it handles creating and managing their lifetimes. Configuring DI in ASP.NET Core happens mainly in program.cs. Step 1. Rendering services. You tell the DI container about your services and their interfaces. You use methods on builder services like builderservices.addScope.productService. Product service, this tells a container. When someone asks for an iProduct service, give them an instance of product service and manage its lifetime as scoped. Step 2. Creating a service typically involves defining an interface, public interface, iProduct service, and a class that implements it, public class product service, iProduct service. Step 3. Injecting dependencies. The most common way is constructor injection. Your product controller's constructor takes iProduct service as a parameter. The DI container automatically provides the registered instance when the controller is created. You can also inject dependencies into other services, not just controllers. Now, when you register services, you specify their service lifetime. This tells the DI container how long an instance of that service should live. There are 3 main options. Singleton. Add singleton. One single instance is created for the entire application lifetime. Every request gets the same instance. Use carefully, mostly for stateless services or configuration objects. Scoped. Add scoped. A new instance is created once per client request, for example, per HTTP request. That same instance is shared within that single request scope. This is the most common lifetime for services like DB contexts or repositories that need to maintain state within a single request. Transient. Add transient. A new instance is created every single time it's requested, even multiple times within the same request if different components ask for it. Good for lightweight, stateless services where you always want a fresh instance. And finally, managing external dependencies, those third-party libraries, also ties into DI. You install them via NuGet.NET Add Package Some Library. Then, if the library provides services meant for DI, you usually register them in program.cs using extension methods provided by the library. You install builder.services.add DB context for EF core, builder.services.add automapper for automember. This integrates them seamlessly into the DI system.
That's a fantastic breakdown of DI. It really feels like the architectural backbone for keeping larger applications sane. Okay, next crucial topic, security. Absolutely non-negotiable. How does ASP.NET handle ensuring only the right people can access things and that they can only do what they're supposed to do?
Absolutely non-negotiable, you're right. Security is paramount. ASP.NET provides robust built-in mechanisms for both authentication and authorization. They sound similar, but they're distinct steps in securing an application. Let's start with authentication. This is all about verifying identity and answer the question, who are you? ASP.NET supports several ways to do this. Cookie-based authentication, common for traditional web apps where users log in with the username and password. The server issues a secure cookie after login, which the browser sends back on subsequent requests. JWT, JSON Web Token, authentication, very common for APIs and SBAs. The client authenticates, e.g. with username and password, gets back assigned JWT, and includes that token in the authorization header of future requests. With an OpenID Connect. Standards for delegated authentication. Allows users to log in using existing accounts from third-party providers like Google, Facebook, Microsoft, GitHub, etc. Your app doesn't handle their password directly. Windows authentication. Primarily for internal enterprise applications, integrates directly with Windows domain accounts, Active Directory.
We touched on implementing JWT authentication for APIs earlier. Just to recap, Step 1, install package, Microsoft.ASP.NET Core.authentication.jwbear. Step 2, configure authentication in program.cs. Use add authentication and add JWT pair, specifying the authority and audience. Also, make sure app.useAuthentication and app.useAuthorization are called in the middleware pipeline in the correct order, authn before authz. Step 3, protect an endpoint by adding the authorized attribute to a controller or specific action method. That's often all it takes to require a valid JWT for access. Now, after authentication knows who the user is, authorization kicks in. Authorization answers the question, what are you allowed to do? It determines if the authenticated user has permission to perform the requested action or access the requested resource. ASP.NET offers 2 main models here. First, role-based authorization. This is simple and common. You assign users to roles like admin, editor, viewer. You might assign roles when a user registers or via an admin panel, for example, using ASP.NET Core Identities User Manager.add-to-role async, user admin. Then you protect resources based on roles using the authorized attribute.
Authorized roles, admin. Authorized roles, admin, editor. Only users in those roles can access it. Second, and often more flexible, is policy-based authorization. This lets you define more granular authorization rules beyond simple roles. Policies can be based on claims, pieces of information about the user stored in their identity, like department, age, or custom permissions, or even custom requirements. You define policies in program.cs, options.add policy, must be over 18, policy, require claim age 18, or maybe policy, require role, admin, require claim department sales. Then you apply the policy using the authorized attribute. Authorized policy must be over 18. This allows for much richer and more dynamic authorization logic. And just briefly on implementing external authentication, Oath and OpenID Connect, like logging in with Google. You'd install the provider-specific package. You go, for example, Microsoft.ASP.NET Core.authentication.google.
Then in program.cs, you call an extension method like add Google with an add authentication, providing your client ID and client secret obtained from Google's developer console. ASP.NET handles much of the complex protocol flow for you.
Right, that covers who can do what. Now, web apps have this inherent challenge. They're stateless. They don't naturally remember anything from one request to the next. So how do we manage Cvader in ASP.NET? How do we make apps remember user preferences, shopping carts, login status? It seems fundamental, yet tricky.
You've nailed the core challenge. HTTP is stateless. Each request is independent. So yes, we need techniques to maintain state across multiple requests from the same user. ASP.NET provides several mechanisms broadly categorized as either client-side storing state in the user's browser or server-side storing state on the server. Let's look at view state first. This is mostly relevant to older ASP.NET Web Forms applications, not really core MVC or Razor pages. View state was a client-side mechanism designed to automatically preserve the state of page controls between postbacks when a form on the page submits back to itself. It worked by serializing the state of controls and optionally custom data into a hidden input field, view state, on the page, usually encoded as base 64. When the page posted back, the server would deserialize this hidden field to restore the control state. Advantages: simple for developers, mostly automatic, didn't use server memory. Disadvantages: could make page sizes huge, increasing load times and bandwidth usage. Only work for postbacks on the same page. Generally avoided in modern ASP.NET development. Next, cookies.
These are small pieces of text data stored by the browser on the client's machine. The browser automatically sends relevant cookies back to the server with each subsequent request to that domain. We have persistent cookies, have an expiry date, survive browser closure, good for remember me, and session cookies, no expiry date, deleted when the browser closes, good for temporary session IDs. Writing a cookie is simple. Response.cookies.append. Username John Doe options. Reading is also easy. Request.cookies username. Advantages: can persist across sessions, work across multiple pages, relatively simple. Disadvantages: size limit, around 4 KB per cookie, total limit per domain. Users can disable or delete them. Potential security risks if storing sensitive data. Always use HTTP only and secure attributes. Often used for session identifiers or tracking preferences. Finally, session state. This is a server-side mechanism. It stores data specific to a user session on the server. Each user session gets a unique session ID, usually stored in a session cookie sent to the client. When the client makes subsequent requests, it sends the session ID cookie back, allowing the server to retrieve the correct session data. Storing data is easy. HTTP context.session.string user tom1 1001. Retrieving is similar. HTTP context.session.getString user d. You can store strings, integers, and even complex objects after serialization. There are different session modes for where the data is stored. In proc, in the web server's memory default, fast but not scalable or resilient. State server, separate server process. SQL server in a database, robust, scalable. Distributed cache like Redis scalable. Custom. Advantages: more secure than client-side for sensitive data, can store larger complex data. Disadvantages: consumes server resources, memory storage, doesn't persist beyond session timeout or server restarts unless using persistent modes like SQL Server Distributed Cache, can impact scalability if not configured properly. Commonly used for shopping carts, temporary user data during a workflow, etc. Choosing the right state mechanism depends heavily on the data, security needs, and scalability requirements.
That's a really thorough explanation of the state management options. It really highlights the trade-offs involved in working around that stateless nature of the web. Okay, last big area, performance. Ensuring our ASP.NET apps aren't just functional, but also fast and responsive. That's critical for user experience, right?
Absolutely critical. Slow applications lead to frustrated users and can impact business goals. ASP.NET Core provides several tools and techniques to optimize performance. Let's start with caching. Caching is all about storing frequently accessed data temporarily in a location that's faster to access than the original source, like a database. This dramatically reduces load on back-end systems and speeds up response times. We have in-memory caching. This stores cached data directly in the web server's own memory. You set it up by registering the memory cache service, builderservices.addMemoryCache. Then you inject iMemoryCache into your services or controllers. Usage typically looks like: try to get the item from the cache, cache.tryGetValue. If it's not there, cache miss, fetch the data from the source, here example, database, then add it to the cache set with an expiration policy, HE_TrackSpire after 10 minutes. Super fast for single server scenarios. For applications deployed across multiple servers, a web farm or cloud environment, you need distributed caching. This uses an external shared cache store like Redis or SQL Server that all server instances can access. This ensures cache consistency across servers. You'd install a package for your chosen distributed cache provider, e.g. Microsoft.extensions.caching.stackexchange Redis. You configure it in program.cs, builder.services.add stack exchange Redis cache, providing connection details.
Then you inject iDistributed cache and use its methods like getString async, setString async to interact with the shared cache, essential for scalable applications. Next up for performance, asynchronous programming, using async and await. We touched on this, but its importance for responsiveness can't be overstated. When your code performs potentially long-running I/O operations, database queries, network calls, file access, using async await frees up the request thread to handle other incoming requests while waiting for the I/O to complete. This prevents thread pool starvation and moves your application much more scalable and responsive under load. It stops the whole app from grinding to a halt while waiting for one slow operation. So you'd write action methods like public async tasky action result get data async. Inside, you'd await calls to other async methods, like await service.fetch data async. And crucially, asynchronous database calls with EF Core are readily available. Instead of context.products.toList, you use await context.products.toListAsync. Most EF Core I/O methods have async counterparts. Using them is vital for performant data access. Finally, some general performance tuning tips. 1. Optimize database queries. For read-only scenarios in EF Core, use ASNO tracking. This tells EF Core not to track the retrieved entities for changes, which significantly reduces overhead and speeds up queries where you just need to display data. Implement pagination properly. Don't fetch thousands of records if you only need to display 20 per page. Use LA and choose skip and take methods to retrieve only the necessary slice of data from the database. 2. Minimize middleware in HTTP payload. Enable response compression. Builder.services.add response compression, app.useResponse compression. This uses gzip or Brotli to compress HTTP responses, reducing bandwidth and speeding up downloads for clients. Configure static file caching effectively, app.useStatic files. Set appropriate cache control headers so browsers cache images, CSS, JavaScript, reducing subsequent requests. 3. Use connection pooling. Databases have overhead in establishing connections. Connection pooling, which is usually enabled by default with EF Core and standard 8.0.NET providers, maintains a pool of ready-to-use database connections. Reusing connections from the pool is much faster than creating a new one for every request. You can often tune pool settings, like max pool size, in your connection string for optimal performance under load.
Wow, those are really powerful tools and techniques. From caching to async to careful query tuning, it really shows how you can craft ASP.NET applications that aren't just functional and secure, but also incredibly fast and efficient. Balancing all that is key to a great user experience. Phew, we have covered a lot of ground today, a true deep dive. From the absolute foundations of ASP.NET, its history, through core architectures like MVC and Razor Pages, comparing core and the traditional framework. Then we got into the essentials, data access with EF Core, building APIs, managing dependencies with DI, tackling security, handling state, and finally, boosting performance. It's been an incredible journey through the landscape of ASP.NET.
It really has. And this whole exploration, I think, highlights more than just a framework. It shows how technology constantly adapts, right? Meeting new demands, cross-platform needs, cloud-native designs, performance expectations. So maybe a final thought for you, our listener. Reflecting on all this, the foundational principles, the modern practices, how might understanding these things empower you? How could it transform your next web project? Maybe let you push some boundaries or even reshape where you want to go with your career in tech. Something to mull over.
Great question. Thank you for joining us on the deep dive today. We hope this exploration of ASP.NET has given you valuable insights and maybe sparked some new ideas. Until next time, keep exploring.